now that we have a pretty good basis for understanding where much of the power of NMR spectroscopy comes from, its extraordinarily high resolution, and the perils of NMR come from the very weak signals that, that we are actually measuring here. And now we're talking about ways we do our experiments to try to maximize the benefits and minimize the problems. We've already talked about locking and shimming, a way to guarantee that our magnetic fields are homogeneous, and therefore the spectra resolution is as high as possible. Now we're going to talk about a little bit how we actually obtain the spectra and some of the fancy mathematical tricks we use to try to minimize the problems we get from such weak signals. There are actually two ways that you could obtain NMR spectra. One of them, the early one, the older method, is called continuous wave NMR. It's not done that way anymore, but it is instructive to get a feel for how it worked. And the best analogy for it I could come up with for you is simply this. Let's imagine that you're now in a new location, one you're not familiar with, and you're interested in knowing where some of the FM radio stations are in that area. I know these days you could simply Google that information and probably wouldn't really care because you're on satellite radio or some other medium instead. But let's, take it back a couple of decades when FM radio is going to be the thing. And you're interested in finding out what are the radio stations between, say, 96 and 104 megahertz on the FM band. Now, one way you could simply do this and kind of make a record of it is to turn on a classic old radio at 96 megahertz, 96 FM, and draw a line on a piece of paper or something representing how much of a radio station, how strong of a signal you're getting. It would be a low line if there's not much there, just a little bit of static. And if you come to a strong radio station, you're going to draw a line that moves up. If it's a modest radio station, it goes up a little ways. If it's a strong radio station, it goes up a lot. It'll actually kind of resemble a spectrum. Now, what we're going to do is actually, carry out a crude demonstration of that process using a classic Stone Age FM radio. This dates back from the era, when tablets were made out of stone and Zaxby's sold pterodactyl wings, but it comes from, things I've done in my past. And so when we're doing this demonstration, I'm going to essentially just be turning on a radio and making a mark representing the strength of the signals that I'm measuring. Anytime you see, what seems to resemble some schmuck's hands drawing the line or turning the radio dial, just remember that's an artifact of the experimental method that we're doing, and you can safely ignore that. So here goes.
So this tech company called Acrobird is working with...
What was I thinking? What South is better? The truck people. Wow. And what a fantastic line.
There. That gets us our nice pretty spectrum. But the problem with it is it took us a fair amount of time. And let's face it, if I wanted to do this more finely, I would have taken more time to do it. I would have turned the dial much more slowly and gotten my drawings much more accurately done. Doing a continuous wave spectrum this way takes a considerable amount of time, and the greater resolution you want, the more time it's going to take. But realize one thing, all of the information that spectrum contains, what frequencies the radio stations are located at, and how strong they are, is essentially a spectrum. It has integration-like information and the frequency information built into it. We could extract, in theory, or get exactly that same information by listening to all of the possible radio stations all at once. Imagine, if you will, you could make that radio play everything between 96 and 104 megahertz. It would sound something like this, which admittedly is not all that pleasant to listen to, but contained within that pile of sounds, that seeming mishmash of stuff, is all of that information. What we need to look for there then is there a way to take that really quickly obtained pile of noise and extract out of it the spectral information? And that's where some really fancy mathematics called the Fourier Transform come into this game. So to introduce Fourier Transforms, ultimately, I'm first going to play with a tuning fork. Now in front of me here I have a microphone that I've attached to one of the Lab Pros from Vernier. One of those things you probably used back there in Gen Chem to be a temperature probe, pH probe, and all the other functions that it had. It also does sound, and what I'm going to show you is the sound waves that this thing captures from things like a tuning fork and a few other items like that. So first what I need to do is to sound the tuning fork and then hold it up to the microphone. Now you yourself will probably not hear anything from the tuning fork. They're not terribly loud, but you'll see on screen the wave pattern that the tuning fork makes as it's being recorded by the probe. So here we go. And you can kind of see that interesting wave pattern that it makes. And so if I do the same sort of thing but with a different tuning fork, this one has a higher pitch. I just want you to see what the difference in the appearance of the wave. Anything for my class. There. Now the real fun of this process comes along not when you're looking at one tuning fork, but when you're looking at a complex combination of sounds, something like a radio playing all the stations at once, something like that. But anyway, what I'm going to do is sound both tuning forks and hold them both up to the microphone at the same time. And I want you to see how the wave pattern is considerably more complex when you have two of these being added together. So here goes. Oh! There. Now, the ultimate of this, of course, is a really complex set of waves and sounds that are all mashed together. And so to show that, you are in the enviable position of being able to listen to me sing a note. So here we go. This is what my voice looks like when all the different sounds are analyzed and put on display. La la la, la la la. I know, I should stick to my day job, and I probably will. Now, you've seen the probe here capture the sound waves, but now I want to introduce you to one other aspect of this, how to get out of these sound waves, particularly the complex sound waves. What are the frequencies of sound in those sound waves? That is what a Fourier transform does. I'm going to show that to you, introduce you to the equation, and then show you how it works.